Welcome back. Now, in order to explain the outcome of the experiments that were performed by Faraday, the three experiments that we studied in previous lectures, in order to explain the outcome or in order to explain the reasons, the physics behind the three experiments that were performed by Faraday, Faraday put forward the laws of electromagnetic induction. Faraday's laws of electromagnetic induction. The first law that was put forward by Faraday was whenever the magnetic field or magnetic flux linked with a circuit changes, an EMF is induced in the circuit. An EMF is induced in the circuit. Before moving ahead and explaining this first law of electromagnetic induction, let me remind you of some basics that we have already covered in the class in previous chapters. You are familiar with magnetic flux. We represent magnetic flux by phi b. We define this magnetic flux in the similar way we define electric flux. As you already are aware that we define flux phi, electric flux phi E, is equivalent to magnitude of electric field E dot area vector A. You can refer to my class notes, where phi E electric flux can also be written as magnitude of electric field, magnitude of area, and cos of theta. If you remember, this theta is angle between electric field and direction perpendicular to area, what you call as area vector. Similarly here, magnetic flux phi b is defined as the product of magnetic flux density B into area vector A. You can also write this as flux phi B is equivalent to B A cos of theta, where B is magnetic flux density, A is area, and theta is angle between magnetic flux density B and perpendicular to area A. If you remember, we had defined this electric flux E as the measure of the electric field lines passing through a particular area. I hope you remember this. Similarly, magnetic flux phi b gives us the measure of the magnetic field lines. What do I mean by measure of magnetic field lines? I will explain this with an example. Let us suppose we have a bar magnet placed over here, where this is say North Pole and this is South Pole. Magnetic field lines outside the magnet will come from North Pole. And finally go here to South Pole. If we take an area, a particular area and place it here, and same area and place it here, the area here is A, area here is A. What are the number of field lines passing through this area and this area? Are the field lines passing through this area and this area same or they are different? Obviously, you can directly tell this from the figure, they are different. Field lines passing through this area A, which is closer to North Pole, is more, and field lines passing through this area A, which is away from the North Pole, are less. By flux phi b, we mean this number of field lines passing through a particular area. So where is flux passing more and where is flux passing less? If I say flux passing through this area, first area, is more, that is more number of field lines than passing through this, and less number of field lines are passing through this. Is this clear? So we basically define flux as the measure of the magnetic field lines. Now what are the units of this flux? This flux phi b is measured in Weber. You can also write its units in terms of B and A. Then you can write flux phi will be measured in. What are the units for flux density? It's Tesla. And what are the units for area? They are meter square. So you can write it as Tesla meter square as well. Fine. Now let's come back to the Faraday's laws of electromagnetic induction. As per the first law of electromagnetic induction, whenever the magnetic flux, now you know magnetic flux, phi b, whenever the magnetic flux linked with a circuit changes, an EMF is induced in the circuit. So one thing that I mentioned in the first lecture as well, you have to remember and you have to keep this in mind. It's not the magnetic field that is producing electric field, no. It's not magnetic field that is producing electric field. Then, it is the change in flux. It is the change in flux. It is the change in magnetic flux that is producing the electric field. I will come to this. So, as per Faraday's law of electromagnetic induction, whenever the magnetic flux linked with the circuit changes, an EMF is induced in the circuit. Now let us try to explain the experiments of Faraday, Michael Faraday, on the basis of this first law of electromagnetic induction. Here it is. In the first experiment of Faraday, he took a coil of say n number of turns connected to a galvanometer G. In its vicinity was placed a bar magnet with north and south pole. As per Faraday, there will be an induced voltage in this coil and then the current flow only when the magnetic flux linked with the coil changes. The flux linking this coil should change. Now one thing will come to your mind. Where from does the flux come and how does the flux change? Let me explain this to you. Since this north-south bar magnet has its magnetic field, so this will produce magnetic flux of its own. Let us suppose flux is in this direction. Now tell me, if you push this bar magnet towards the coil, the flux, that means the field line, magnetic field lines passing through the coil, will they increase or decrease? Or they will remain same? They will definitely increase. Because when you push it towards this, you are pushing this bar magnet towards the coil. The number of field lines, more number of field lines will now pass through the coil. That means whenever you push this bar magnet towards the coil, the magnetic flux, that means the magnetic field lines that were passing through this coil, they change. When the magnetic flux or the magnetic field lines passing through this coil change, according to Faraday's first law of electromagnetic induction, there will be a voltage induced in this coil. And when this voltage is able to produce the current in the circuit, if circuit is complete, that voltage will generate a current in the circuit. That current will flow through the galvanometer and galvanometer shows deflection. Fine. Next. But if we move this bar magnet away from the coil, what happens at that time now? You are not pushing magnet towards the coil, you are pulling it away from the coil. Initially, when it was in this position, there were a number of field lines which are passing through this coil. Fine. Now, when you pull this away from the coil, the number of field lines passing through the coil, will they change or they will remain same? They will definitely change. Now they will increase or decrease? They will decrease. So whenever you are pulling this bar magnet away from the coil, the flux passing through this coil changes or that decreases. And according to Faraday's law of electromagnetic induction, it does not increase or decrease of flux that produces. No, it has not to be either increase or decrease, any change. If it increases, it produces the EMF over here. If the field line through the coil decrease, it produces the EMF over here. That means the only condition that need to be satisfied is the number of field lines passing through this coil should change. Number of field lines passing through this coil can be changed either by pushing this magnet towards the coil or pulling this coil magnet away from the coil. In either case, you are changing the field lines passing through this coil. When you are changing field lines or flux passing through this coil, an EMF E will be induced in this coil, which will produce a current in the coil. That current will be detected by galvanometer. This is how we explained first law, how we explained first experiment based on Faraday's law of electromagnetic induction. Now let's come to the second experiment. If you remember, in second experiment, what we did, you had a coil over here connected to a galvanometer You had another coil over here connected to voltage source V through a resistance R. So there's current flowing in this circuit. When there is current flowing in this circuit, a current carrying coil behaves as a magnet. So it will produce its magnetic field. So this magnetic field, suppose in this direction. This in this direction. Now, if you push this coil towards coil C2 towards coil C1, will the magnetic field lines, mark my words, if the magnetic field lines passing through coil C1 change or they will remain same? Definitely they will change. When you push C2 towards C1, the field line now passing through C1 will increase. If there are like two coils are side by side to each other, very close to each other, like the flux produced by this coil, all the flux is going through this. Initially, suppose the two coils are away. Now, when you are pushing this second coil towards the first coil, the flux produced by the second coil, field lines producing by the second coil, more and more field lines produced by the second coil will pass through the first coil as well now. So whenever you push the second coil towards the first coil, the flux or the field lines passing through C1 changes. Similarly, if you pull this coil C2 away from coil C1, in that case, what happens? The field lines passing through C1, though C2 produces same field lines because the magnetic field of C2 is same. That depends upon the current, and current is constant. Field of C2 is same, but the flux or the field lines passing through C1 changes. When you pull this away from C1, the field lines flowing through C1 decrease now. When field lines flowing through C1 decrease, we know as per Faraday's law of electromagnetic induction, whenever field lines change, here a voltage will be induced and EMF will be induced. That EMF will produce a current, and that current is being detected by galvanometer. Fine. This was Faraday's second experiment. And what about Faraday's third experiment? Let's come to the third experiment of Faraday now. In Faraday's third experiment, we are not moving any of the two coils. This is a very interesting case. We are neither moving C1 nor moving C2. Both C1 and C2 are stationary at their own places. Then how is voltage being induced in coil C1 and galvanometer showing deflection? Look here carefully. Initially when this switch was open, what was current through this coil? 0. What was magnetic field produced by this coil? 0. What was magnetic flux produced by this coil? 0. What was the flux? What were the magnetic field lines produced by this coil? 0. What were the magnetic field line linking this, passing through this coil? 0. Because ये produce ही नहीं कर रहा, it's not producing magnetic field at all. If it's not producing magnetic field, it's not producing flux. When it's not producing flux, there is no flux linking to this. Fine. Now you close switch. When you close the switch, initially what was this current? Initially I was 0. When you close the switch, this current will start to increase. Initially it is 0 and finally it will become I. When this current was 0, what was magnetic field here? 0. What were magnetic field lines produced by this coil? 0. But now when you close the switch, the instant you close the switch, current starts to increase. This current will start to increase and finally this current will become equal to I. When this current starts to increase, the magnetic field starts to build up. So magnetic field starts to increase. When magnetic field starts to increase, the magnetic flux produced by this starts to increase, or magnetic field lines produced by this increases. When magnetic field lines produced by this increases, initially here magnetic field lines was 0, number of field line linking here was 0. But now this is producing some magnetic field, so this is producing some magnetic field lines. The number of field lines passing through this coil C1 will be 0, or they will start increasing. They will also start increasing. That means when current starts to build here, or magnetic field starts to build here in this coil, the flux passing through this coil also changes, also increases. And finally, this current will reach value I in a very small amount of time. This current becomes value I now. The switch is closed. Is this I constant now? Is this changing? This is a constant value. Initially it was 0, then it was increasing gradually. Initially it was, this is time, this is current I. Initially this current I was 0, then this current I increased, and finally it becomes constant. Now when this current I is constant, so magnetic field produced by this coil is constant. The number of field lines linking this coil is constant. Why? Because there is no change in magnetic field over here. Neither are you moving through coils. So number of the field lines produced over here, a portion of that will link this coil. But that number is constant now because magnetic field is not changing. When magnetic field is not changing, the field lines through this is constant. So now this won't produce any voltage because there is no change in flux over here. Initially during this time, when current was increasing, at that time, magnetic field over here increased, flux here increased, so field lines through this increased. So there was a voltage induced over here. Then current became constant, field here is constant, field lines passing through this is constant. When field lines are constant, no voltage is induced. Voltage is induced only when the flux linked with the coil changes. When flux is constant, it does not change, so EMF is not induced. So EMF was induced only during this time. During this time when current was increasing. Similarly, let us suppose after some time, you're opening this switch now. Initially this was value of current. When you open the switch, current will start to decrease and finally the current will become 0. The instant when you turned off the switch and current starts to decrease and finally current becomes 0. During this interval, this current is decreasing. When this current is decreasing, magnetic field produced by this coil is decreasing. Magnetic field produced by this coil is decreasing, the field lines produced by this coil is decreasing. When field lines decrease, field lines produced by this decrease, field lines passing through this will also decrease. So when here field lines passing through this is decreasing and EMF will be induced in this coil, that induced EMF will produce a current in this coil. So this galvanometer G will record the current. Is this clear? So this is how Faraday explained all the 3 experiments based on the Faraday's first law of electromagnetic induction, which say whenever the magnetic flux linked with a coil changes, an EMF is induced in the coil. This was Faraday's first law. Now what is Faraday's second law? Faraday's first law was concerned about whether EMF will be induced or not. And now we know EMF will be induced only if the flux passing through that coil is changing. Fine? And Faraday's second law is concerned with the magnitude of EMF. How much voltage will be produced? Is this voltage all the time same? Or does it depend upon something? According to Faraday's second law of electromagnetic induction, the magnitude of EMF induced is equal to the rate at which the magnetic flux phi b through the coil or loop changes. What this means is, if you move this north pole towards the coil, the field lines through this change. It will produce a voltage, so this will show a deflection. But how much deflection will this produce here depends upon how much voltage is induced over here. And what are the factors on which the voltage induced in the coil depend? According to Faraday, the voltage induced in the coil is directly proportional to the rate of change of flux. If you are changing this flux very fast, what produces voltage over here? It was change in flux. Now if this change in flux is fast, you are changing flux very fast, so this induced voltage is more. If you are changing flux slowly, this induced EMF is very small. Are you getting me? That means voltage induced in this depends upon the change in flux. And the value of that voltage, how much will be the voltage induced over here, that basically depends how fast or how slow you move this. How fast or how slow you change the magnetic flux. In other words, we can say, if we move this north pole slowly towards the coil, it will induce voltage, it will show deflection. Now if we move this north pole very fast towards the coil, it will again change the flux, and this galvanometer show more deflection because more flux will be induced. So mathematically we can say, as per Faraday's second law of electromagnetic induction, induced EMF is directly proportional to a rate of change of magnetic flux. We write induced EMF by E. Induced EMF E is directly proportional to. What does this mean? Rate of change of magnetic flux. We know magnetic flux is phi B. Rate of change of means d divided by dt. How much flux is changing with respect to time? This is known as rate of change of flux. One more thing. This induced EMF E here will also depend upon the number of turns. More the number of turns, more will be the induced EMF. So you can write this induced EMF E is equivalent to n number of turns into d phi b by dt into rate of change of flux. This is Faraday's second law of electromagnetic induction. So we can write this as E is equal to number of turns n into d phi by dt. I will send you the notes on your respective emails in a day or two. So these are two very important laws. Faraday's law of electromagnetic induction. You may have a question now. Sir, what will be the direction of this induced EMF E? Will current flow in this direction or will current flow in this direction? What will be the direction of current or what will be the direction of induced EMF? We'll come to that. That's given by the Lenz's law. We'll come to that in next lecture. Till now, what we have studied is Faraday's two laws of electromagnetic induction. First one tells that whenever the magnetic flux linking through a coil changes, an EMF is induced in that coil. Second says about the magnitude of that EMF. EMF induced E is directly proportional to the rate of change of flux and is also proportional to number of turns. Fine. This is a very beautiful equation over here. Now we know that induced EMF E is equivalent to n number of turns into d phi p divided by dt. Let's look here. In second experiment, if you keep this coil stationary, you keep this coil stationary. There's a current flowing through this second coil, current I, equal to V by R. Will this current produce a magnetic field? Definitely it will produce. Will that produce a flux? It will produce a flux. Will a part of that flux link this coil? I mean, will a part of that flux also pass through this coil? It will pass through this coil as well if it's near to it. If it's very far, it may not. Then value may be very small. So a part of flux is passing through this. So will it produce voltage over here? No, it won't. Why? Because E does not depend upon the flux. Then E depends upon the rate of change of flux, d phi by dt. E is not induced because of flux. Then E is induced because of the change in flux. This flux should change. How can you change this flux? One way of changing the flux is you either move this coil here towards coil C1. You are increasing the flux. That means you are changing the flux. Or you move this coil away from this. In that case, you are again decreasing the flux through this. You are changing the flux. These are the two methods. Fine. Now, how can we change this flux? How can we change this flux? What are the methods of changing the flux? We already know this flux phi B is equal to B A cos of theta. So you can change this flux phi B either by changing B, that is magnetic flux density, or you can change flux phi B by changing the area of the coil. Or third, you can change this flux phi B by changing angle theta, that is orientation. So you have three ways of changing flux phi B: by changing the magnetic flux density B, by changing the area vector, by changing the area A of the coil, or by changing the orientation of the coil. What I mean to say is, we'll continue in next lecture. I just want to give you a brief overview. What I mean to say is, let us suppose you have a magnetic field on this side. You have north on this side. You have south on this side. And I have a coil over here. With a galvanometer connected. How can I change flux passing through this? There are three ways of changing flux. Either you have to change flux density. How can I change flux density? By either moving this coil towards the magnet or moving it away from the magnet. We know magnetic flux density is maximum here. It's maximum here. It's decreasing. As we go away from the North Pole, flux density decreases. That means if you take this coil towards North Pole, B is more. If you take this coil away from North Pole, B is less. That means you can change the flux through this coil by changing the flux density B, by moving it either towards the magnet or away from the magnet. I won't be discussing area here, but we can change area as well. How we can change area, I'll come to that in the future lectures. And how can we change the orientation? By orientation, I mean, suppose you have North Pole on this side, you have South Pole on this side. Fine. You keep a magnet like this. You keep a coil like this. You have a coil here and you have a magnet here. If I change the flux is passing through this coil here. If I change the orientation of this coil, suppose I am moving this coil to this shape now. Flux passing is zero, there's no flux passing. When this coil was in this orientation, flux was passing through the coil. When you tilt this, you tilt it, less flux is passing, less flux, less flux, less flux. Finally, zero flux is passing through this coil, all the flux going this direction. Are you getting me? Okay. We'll continue in next lecture.